non-electrolytes. So let's just review what we discussed a few minutes ago. All soluble ionic compounds are electrolytes. Let's go through a few examples. As we showed, sodium chloride, table salt. Table salt is a strong electrolyte. Potassium nitrate. Once again, if you're confused on the question, let's see how this would break up. If we broke up potassium nitrate, we would get potassium cations in the polyatomic ion, the nitrate ion. These break up into ions, and this would act as an electrolyte also. It would cause our light bulb to illuminate. Other forms, other types of electrolytes, these are all electrolytes so far. Other electrolytes are strong acids and strong bases. And this is where we start to classify electrolytes as being either weak or strong electrolytes. Strong electrolytes include sodium chloride, potassium nitrate, strong acids, and strong bases. Weak electrolytes, how we can further classify an electrolyte. Weak electrolytes are going to be weak acids and weak bases. The reasons why weak acids and weak bases are weak electrolytes is that they don't ionize completely. They don't break up completely. Now, we're going to spend some more time later in chapter 4 on acid-base neutralization reactions. We did discuss one last week when we did our stoichiometry problem. You'll learn a lot about acids and bases in the second semester of Gen Chem, but for now, we're briefly going to go over some of the properties of acids and bases and focus on the differences between strong acids and strong bases being strong electrolytes because they break and ionize completely, and weak acids and weak bases as being weak electrolytes. They don't break up completely. Now, to understand about acids and bases, we need to introduce some terminology and some definitions. How do we classify or define whether a substance is an acid or a base? Several definitions do exist. One common definition that we have that's usually discussed in a general chemistry class is the Arrhenius definition. Now, Arrhenius, real important guy, Swedish chemist, physicist, he gave us a definition for an acid or base, and what he focused on was the ability of a substance to give up hydrogen ions or increase the amount of hydroxide ions in water. So let's look at the Arrhenius definition. Arrhenius defined an acid as being a substance that increases the hydrogen ion content in water. Arrhenius defines a base as being a substance that increases the hydroxide ion concentration or content in water. For our discussion on aqueous phase solutions, this is a really good definition because it focuses on water. But we do have a broader definition that you'll learn better about in the second semester of Gen Chem, and that's what we call the Bronsted-Lowry theory. Now, remember, Arrhenius focuses on the hydrogen ion content increasing for an acid and the base as increasing the hydroxide ion content of water. We're going to show in a few minutes that this is important when we start to learn how to identify an acid or a base by looking for hydrogen or hydroxide. And we're going to introduce that in a few minutes. But first, let's discuss a little bit about the Bronsted-Lowry definition. The Bronsted-Lowry definition, these were two scientists that worked independently, but they developed the theory around the same time. Bronsted-Lowry definition defines an acid as a substance that can act as a hydrogen ion donor. We sometimes call this a proton. If you recall, the hydrogen atom has a single electron and a single proton and no neutron. The hydrogen ion has lost its single electron, and we're left essentially with nothing more than a proton. Bronsted-Lowry defines a base as a hydrogen ion or a proton acceptor. So this is somewhat broader of a definition because all it deals with is the acceptance or donation of the hydrogen ion. Doesn't require hydroxide ion, such as we showed in our Arrhenius definition. Now, there are, based upon our definitions and what you need to know, there are 6 strong acids. 6 strong acids. Strong acids are strong electrolytes. As we showed for sodium chloride, strong electrolytes break up completely. Strong acids break up completely also. And there are 6 of them that you need to know. HCl. We'll go over how to name these later today. HBr. HI. HNO3, HClO4, and H2SO4. We'll learn their names more when we go into how to name acids and terminology. Now, if we took some HCl and put it into water, HCl would break up completely they ionize or break up, dissociate into positively charged ions and negatively charged ions. And like the sodium chloride, it would cause our light bulb in our experiment to illuminate pretty brightly. So these are the 6 strong acids you need to memorize. If an acid is not on this list, it's a weak acid. And we'll discuss those in a few minutes when we introduce weak acids as being weak electrolytes. There are also strong bases that you need to know. Now, strong bases are our metal hydroxides. Strong bases, metal hydroxides, make up these strong bases. It's a metal, important, it's a metal with a hydroxide. Some examples of these: lithium OH, strong base. Sodium OH, potassium OH. These are 3 of our alkali metal hydroxides. There's only one alkaline earth metal hydroxide that I am going to be working with, and I want you to know. And that's barium hydroxide. Notice for every barium ion, there are 2 OH groups. That's because if we break this up, barium, as you recall, is a group 2 alkaline earth metal. It has a positive 2 charge. Each hydroxide group is -1, and we would need 2 of them for each of our bariums. So this would break up such as that. These are all strong electrolytes. If we put them into water, they break up into their ionic components, and they would conduct electricity. Notice they have charge carriers, a positively charged species and a negatively charged species. They would conduct electricity in water, and they would cause our light bulb to illuminate as a strong electrolyte would be expected to. Weak electrolytes. This is where we differentiate our electrolyte strength. As we said, strong electrolytes are any ionic compound that dissolve in water completely. Strong electrolytes, strong acids and strong bases, strong electrolytes. Weak electrolytes are going to be our weak acids, weak bases, and water. Tap water, for instance. These are weak acids, weak bases, and water itself is a weak electrolyte. You'll learn in Gen Chem 2 that water does ionize or break up to an extremely small extent, and water is a weak electrolyte. Now, some examples of some weak acids. Acetic acid. Is a weak acid. It's not on our list. If we put acetic acid into water, it only breaks up to a small amount. Weak bases. Ammonia is a weak base. If we put it into water, it will accept some of the protons from water acting as a base, and it's going to give us a small amount of hydroxide, and this would actually form the ammonium ion. Water itself ionizes to a very small extent. So, as you recall, we discussed a little bit about HCl, if we dissolve that in water. How about let's classify water even more. How about tap water? Versus deionized. Which of these are going to be the weaker of the two? They're both weak electrolytes, but one is actually weaker than the other. Now let's think about deionized water. Deionized water, that's the water that we usually use in lab. Not usually, but we're going to use it for every experiment that we do. What we have is we have filters, and we have a method of removing ions. Deionized water, if we put a light bulb over it, we put a little light bulb here, man, we might get a flicker, if anything. How about tap water? How about tap water? Now, tap water comes right out of our sink. Tap water, a lot of communities put sodium fluoride into tap water for your teeth. There might be some rust in tap water. Tap water has a rich source of ions in it. If we put a light bulb over tap water, it's probably going to illuminate to some extent greater than if we had deionized water. So tap water is a weak electrolyte. Deionized water is even weaker because there's no ions, where tap water has a limited amount of dissolved ions in its environment. Let's go over a exercise. Review exercise to see which ones we can predict are weak electrolytes, strong electrolytes, or non-electrolytes. So let's answer a few questions. Again, these are like exam type questions. Let's look at 4 compounds, and let's predict if we have an electrolyte, weak electrolyte, or a non-electrolyte. Some of them we've already discussed. Potassium nitrate, we already discussed it. If we put potassium nitrate into water, we get potassium and nitrate ions. And this is a strong electrolyte. Breaks up completely, ionizes completely. Sodium hydroxide. It's a strong base. If we put sodium hydroxide into water, we get sodium ions and hydroxide ions, and this would be a strong electrolyte. HF. Very similar to the acids we showed earlier, but it's not a strong acid. It's not on our list. HF is a weak acid. It's not on the list of our 6 strong acids. We usually use a double-sided arrow to represent that this breaks up into a small extent, whereas some of it forms its fluoride and hydrogen ion, but some of it recombines and it stays as HF, non-ionic solution. But a small extent of it does break up into the ions. This is a weak acid, and it's a weak electrolyte. It ionizes to limited extent. The light bulb would be kind of dim. It would illuminate a little bit, but not much. How about methanol? CH3, that's just OH. This is methanol. It has a hydroxide, but that's not a metal hydroxide. This is an alcohol. It's an organic compound with an OH group on it, not a metal with an OH. This is an alcohol. It's a molecular compound, and it's a non-electrolyte. It's not going to break up into individual ions. If we had a light bulb attached to it, it's not going to illuminate. So those are some examples of predicting whether a compound is a strong electrolyte, weak electrolyte, or a non-electrolyte. So we're going to move a little further into chapter 8.4, and we're going to discuss another important topic, and that's solubility. Solubility is defined as the degree to which a substance dissolves in a certain solvent at a particular temperature. What you need to do in this section is predict if a solute is going to be soluble in water. And you're going to be using solubility rules. There are tables out there that you'll have available to you, but I want you to know how to use the tables. Otherwise, it's useless information. So we're going to focus on ionic compounds that dissolve in water to a small extent or to a great extent. And what we want to do is to make a prediction whether this substance is going to be soluble or insoluble at a particular temperature. So, and if you take the second semester of Gen Chem, you're going to learn some quantitative ways to determine solubility. What we learn in Chem 1110 are solubility rules. It helps us to make predictions as to whether an ionic compound, when we put it into water, will dissolve into ions, or whether it's going to stay in its solid state and not dissolve into ions. So, chapter 8, table 1. Table 8.1, I'm sorry, is a good reference for solving problems. Now on this table that you have, you're going to use it such as this. Now, if you look at a table of solubility rules, these are solubility rules. Let's know how to use them. Now, if you look at the solubility rules, they give you a list of soluble compounds. Soluble compounds. And they have another column on this table that tells you about insoluble exceptions. Put a line here just to help us. Insoluble exceptions. And on the top part of the table, they look at cations. So if you notice how this is set up, they have cations. And remember, these are going to be positively charged species. And on the bottom of the table, they look at anions, negatively charged species. And let's look at a few of these entries. On the top, up here, we have our alkali metals. These include lithium, sodium, potassium, and several others. All of our alkali metals, and they have no insoluble exceptions. In other words, if you have a compound and it's composed of an alkali metal as the cation, it's always going to be soluble in water. That's important. down here, anions. Nitrates, always soluble. They also have chlorates. And up here also they have the ammonium ion. Ammonium ion, always soluble. These guys are always soluble. Those are the anions that are always soluble also. And we also have some that have exceptions. So without exception, these are the cations and the anions. With no exception, they're always going to be soluble. Then we have the ones that are fun. These have exceptions. So let's look at some of the other compounds that we have. So with no exception, these are always going to be soluble. Halides. Now our halides include chloride, bromide, and iodide. Fluoride, they usually don't have one. Fluoride's very reactive in water. Now, these are going to always be soluble with the exception silver, mercury, and lead. So these ones get kind of tricky. And we also have our sulfates. Sulfates are also normally sulfates, and they also have a few exceptions that are on our list. So these are the compounds that are normally going to be soluble. These ones are always soluble. These are soluble unless we have these exceptions over here. And then we have another list that have insoluble compounds. Now, most of our insoluble compounds are always going to be insoluble unless they're in the presence of our alkali metals or the ammonium ion. And I would refer to those lists as you're working through these problems. Let's do a few examples. Nickel sulfide. So nickel sulfide. Soluble or insoluble? So if we break this up into its individual ions, we would look on our list here, and what we would find out is that most of our sulfides are insoluble. This compound has sulfide in it. This isn't an alkali sulfide, alkali metal sulfide. So this compound is insoluble. Let's look at our next example, lithium carbonate. Here's lithium. Here's carbonate, and this forms lithium carbonate. So when this breaks up into lithium ions and carbonate ions. Soluble or insoluble? Notice it's breaking up into alkali metals. Lithium is a soluble alkali metal. Lithium carbonate is composed of lithium. Therefore, we expect this compound to dissolve in water, and this is soluble. Magnesium phosphate. Now, if we break up magnesium phosphate, we would see that phosphates are insoluble. This isn't one of our exceptions, so this is insoluble. It's composed of a phosphate. Phosphates are normally insoluble. The last one, ammonium chloride. Since this is composed of a compound with ammonium and it has no exception, we expect this to be soluble. In other words, we're going to get ammonium ions and chloride ions in solution. So those are our rules for using, those are how we use solubility rules to help us solve problems. And there's a similar example on page 331 that you should look over. Now, we use solubility rules to help us understand what's happening in one reaction type that we're going to look at. Our next few sections, chapter 8.5, 8.6, 8.7, involve reaction types in an aqueous environment. The first reaction type we're going to look at is in chapter 8.5. We're going to use solubility rules to predict the outcome of a precipitation reaction. And that's the topic in chapter 8.5 that we're going to use and discuss. Solubility rules are important, and we use solubility rules to make predictions about a precipitation occurring or not occurring. So chapter 8.5 involves precipitation reactions. So that's our big topic in chapter 8.5. What you need to do in this section is to take a look at a combination of two aqueous solutions that have ions in it and make a prediction as to whether a precipitate is going to form. And we're going to use our solubility rules to make these predictions. Now, a precipitation reaction is common if we take two solutions that have ions dissolved in them, and if we combine them, do we form a solid precipitate? I was going to draw this on the board and go through some really bad pictures that I can't do too well, or you're in for a treat, we're going to do a demonstration to help us predict what happens during a precipitation reaction. We're going to look at two solutions. And we're going to understand a little bit about what's happening. And at the end of this exercise, we'll go through some simple examples. And later, we're going to go over this example right here. So we're going to look at it first, describe one that's a little bit easier. And when we're done, I want you to be able to write what's happening in terms of an equation. So we're going to take two solutions, two aqueous solutions that have dissolved ions in them. And we're going to conduct what we call a partner exchange or a metathesis reaction. So essentially what we're doing is taking two solutions that have ions, and we'll call this solution AB. It has a cation A and an anion B. And it's dissolved, and it looks clear. It doesn't look like anything's happening. And we're going to add it to another solution. And this solution also looks clear. And this is composed of another ionic compound, CD. C would be the cation, D would be the anion. And we're going to combine these into one large environment. And what we need to mention about this first case, these are cases in which both A and B and C and D are are soluble. They're completely dissolved ions in solution. We're going to recombine these two solutions now, make one big one. And what we're going to do is exchange partners. This is the idea behind a partner exchange reaction. Partner exchange. A bigger word for this is a metathesis reaction. It means the same thing. Metathesis. Hope I spelled it right. Metathesis reaction. Or we sometimes also, there's another name, double displacement. All of these mean the same thing. So you know what? I am drawing a picture, then we'll do a demo, just so you get so you get more out of it. So let's think about partner exchange. We combine these two beakers and we put them into this environment. What we're going to look at is if we put A and B into an environment and we break them up into A and B ions, because over here, they're ions in solution, they're completely soluble, and C and D is completely soluble also. What we're thinking about, would A have the propensity to combine with D to form a precipitate? Or would C form with B to form a precipitate? That's the partner exchange we're looking at. Would A combine with D and C combine with B? At the end of the process, are any of those going to form a solid precipitate? Because right now, when we add them, we would have an AQ. They're all ions dissolved in solution. When we combine them, does one of them form a solid precipitate? Would we put an S here and this be aqueous? Or would these stay as ions in solution and this form a solid? And we can also get the case where none of them form a precipitate. In that case, we get no reaction. So that's the goal. We're going to use solubility rules to see if we recombine our ions, do they form a solid precipitate? So what do precipitates look like? That's a good question. So if you're following along with my PowerPoint, this is, we sort of jumped around a little bit, but we're going to do our demo now. So I need to put on some goggles, pull out the table here, and we want to look at what's happening in a real case situation. I'll write it down up here and we'll save it for a little bit. At the end of today's experiment, as an exercise, I'm going to have you write this and we'll go through it in our next lecture. How's that? Keep coming back for more. Because this one's kind of complex. We're going to write a simple one first. I need my goggles. Ooh. Looking pretty good. I like that. So we're going to do a partner exchange process. And I'm going to show you the two reactants that we have. And we have in our one beaker, in beaker one, and it's this one. If you can't read that, that's calcium carbonate. Calcium carbonate is in an aqueous solution, and we're going to add that to ammonium oxalate. Notice both of them are pretty clear. They don't look like anything's happening. That's ammonium oxalate. I'll write down its formula. Okay. So they're both aqueous ions suspended in solution. Nothing happening, it looks like. So here's the calcium carbonate. I'm going to bring that down there so you can all see it. There's calcium carbonate. And I'm going to put that into the speaker. Clear, nothing happening, nothing happening. Now here's our other ammonium oxalate. Let's add that. Whoa, something happened. Something just happened. That's what we mean by a precipitation reaction. We added two solutions that look optically clear as if there's nothing going on. We combine them and we get some white film forming, or a cloud, or a solid. What would happen if I let this sit overnight? This would probably form a solid layer on the bottom. Maybe I'll save it and bring it back. If we let this sit overnight, this would probably form a layer on the bottom. And what this is an example of a precipitation reaction. So we would use a double displacement to write the overall process that's occurring. Good. You would use solubility rules. You might need some really good solubility rules. You might have to look up on the internet on this one. A little more difficult because those ions that we had, probably not on that table. So that's the idea of a precipitation reaction. Let's go through how to write. I'm going to put this aside so I can take off my goggles and you can. Don't need those. Okay. At the beginning of next lecture, we'll go over this. I want you to try writing that but first we need to know how to do it. So this will be the complex reaction that we're going to work on at the beginning of next lecture. But let's just finish this lecture by discussing a double displacement and how we write this type of process out. Let's use a simpler example as our model, and we'll return to this one. Because you're going to have to look up some information on the internet on your own. We're going to take, just like we did, we're going to take a solution that's composed of sodium chloride. And we're going to add it to a solution that has silver nitrate. I don't have these with me today. I actually was looking for it, couldn't find any. And just like we showed in our last process, they would look clear. It would look like nothing's happening in these two environments. And we would combine them into this large environment. And then what we would do for this type of reaction is we're going to exchange partners. Okay, what's sodium chloride? Well, sodium chloride, as you recall, are sodium ions and chloride ions. AQ tells us that those ions are floating around in water. It doesn't stay as a solid sodium chloride clump. They break up into ions. That's what AQ is telling us. It does tell us that. Silver nitrate, AQ, tells us that these are silver ions and nitrate ions. Let's add them all to this environment. What are the products we would get? Well, now what we're going to do is a partner exchange. Notice in this environment, there's just sodium and chloride ions. So what are we going to get over here? Well, there's a possibility sodium nitrate could form. Put that there, sodium nitrate. And we can also get an exchange of silver and chlorine, silver chloride. So that's the partner exchange as we're writing it. Now we're going to use our solubility rules. We would turn to our table that we would have available to us, and we would look at sodium nitrate. Let's think about sodium right away. What's in sodium nitrate? It's an alkaline metal, sodium, and remember, alkaline metals are always going to be soluble, and therefore this is without exception, this is going to stay aqueous ions in solution. Sodium nitrate, an alkaline metal, combined with nitrate. All nitrates are soluble. That's a soluble compound. Let's look at silver chloride. Remember in our table, chlorides, usually our halides are going to be soluble. An exception is silver halide. Silver chloride is insoluble. And we would write an S by that to represent that as our precipitate, silver chloride. And that's how we use solubility rules to write an equation that represents a precipitation reaction occurring. So this equation, as we've written it, there's actually a name for this. This is sometimes referred to as the molecular equation. I've seen other books that call it just the chemical equation. One reason why some books call this the molecular equation is that it sort of makes them look like they're all combined in solution. Like this is combined, even though they're not. They're sodium and chloride ions. This is silver and nitrate ions floating around. This is sodium and nitrate ions floating around. This is silver chloride, a solid that would form a milky appearance, or it would fall down to the bottom of that container as a solid. So it's really not compounds that stick together when we have an AQ. Only the solid stays as a solid in solution. So we can actually improve on this definition. We can write what we call an ionic equation. So let's write an ionic equation. Ionic equation breaks these into individual ions. When we have an AQ written in parentheses by that substance. So the ionic equation gives us a better representation as to what's happening in solution. AQ tells us these are silver cations and chloride ions that are floating around in this environment. This is silver ions. And this is nitrate ion. It doesn't break up any further. It's NO3 negative. Let's look at our product side. Notice there's an AQ. AQ tells us that this is sodium ions and nitrate ions, all floating around in solution. This is silver chloride solid. Notice the S, it doesn't say AQ. These are not ions floating around. This is a solid silver chloride that's forming a precipitate, and we do not break it up any further. The S, as we've predicted from solubility rules, tells us that we're forming a solid precipitate. And this is called the ionic equation. We can improve even a little bit more by writing what we call a net ionic equation. Net ionic equation. When we write a net ionic equation, we get rid of something that we call spectator ions. Spectator ions are ions that are ions on the reactant side and product side. What we can think of is they're staying as ions dissolved in solution, not really doing anything at the beginning of the reaction and at the end of the reaction. Let's find where our spectator ions. Notice sodium is an ion on a reactant and product side. Nitrate is an ion on our reactant and product side. Those sodium nitrate ions are our spectator ions. They don't participate in any chemical reaction. They simply stay as ions in solution. Let's write the net ionic equation. Now, by convention, we usually write the cation first. And that would be our net ionic equation. The net ionic equation really tells us a lot about the chemistry that's occurring. We're adding silver ions and chloride ions to form a silver chloride precipitate, indicating that a chemical reaction has occurred. Remember, we said that that's one of the indicating features of a chemical reaction, the formation of a solid substance. So that's pretty much it for today. I just wanted to show you one other thing. Oh, let's try one more problem. This is something I said earlier. What if I combined sodium chloride and potassium nitrate? We did a partner exchange. And if we would use solubility rules, we would see that potassium is always soluble. It's an alkali metal. Sodium nitrate is also soluble. In this case, since there's no precipitate forming or anything else forming, there's NR, no reaction occurring. So if we do a partner exchange and we form species that are soluble, guess what? No reaction has occurred. So just before we end, I wanted to show you what we got here from this precipitate. Remember I said it might sit on the bottom? I'm going to tilt this down. And maybe you can see how that's starting to settle on the bottom of that environment as a solid. We let it sit long enough, it starts to settle to the bottom. And that's one way we can collect a product. We would filter it off if we were collecting this as our example. We'll start next lecture by considering the ionic and the net ionic equation for this reaction. We had calcium carbonate plus ammonium oxalate. Might have to look up oxalate to see how that is performing in this process. You need to find some solubility rule. I wouldn't give that to you on an exam. I would give you one that has solubility rules that you could look up. Find out what's happening here and write the ionic and the net ionic equation and find out what the spectator ions are. Any questions? Give me a shout. Good luck and have a nice rest of your week. We'll get back to you guys on Thursday. Thank you.